this session. So that is because this portion is very important so that you can revisit it. Okay.
All right.
So we discussed energy in simple harmonic motion. So it was like that at the mean position, as you can see, kinetic energy is maximum. Okay, but potential energy is zero. And at the maximum amplitude, potential energy is maximum while kinetic energy is zero. That means its velocity is zero. We know the displacement equation is given as x is equal to a cos omega t plus phi. And the expression for kinetic energy is half mv square. And we derived the velocity equation from this displacement equation, and that was a omega sine omega t plus phi. That is just the differentiation of this displacement equation. So after that, we'll end up with this equation. This is the kinetic energy. So remember that the period of kinetic energy is T by 2 and the frequency is twice is that of the oscillator. Here the force is conservative force, okay, because F is minus kx. It is always directed towards the mean position, alright. And
Okay.
potential energy is given as U is equal to half kx square. And x was, again it was a cos omega t plus phi. So just plugging this value here, we'll end up with this equation. So total energy will become potential energy plus kinetic energy, and by plugging these values here, we'll end up with this equation. So this is the total mechanical energy of a oscillator, right? Alright. So total mechanical energy is independent of time, as you can see from this formula, as expected for motion under any conservative force, right? Now let's move on. Alright. So the total mechanical energy is independent of time. Now let's discuss its graph. Okay. The time and displacement dependence of potential energy and kinetic energy of a linear harmonic oscillator. So if you draw the graph, it looks like this. Here this axis represents energy and this axis represents time. Okay, so the graph looks this way. The period is T by 2 as mentioned earlier, right? This is T
Right.
by 2, this is 0. So here one is kinetic energy and another one is potential energy, okay? So let's say this green one is the kinetic energy. So when kinetic energy is zero, potential energy is maximum, right?
Yes.
At this point, potential energy is maximum. Sorry, kinetic energy is maximum, but here potential energy is zero. So this is the relation of energy, okay, and its period is t by 2, right? So it is occurring after t by 2. This is the, so as you can see, this is the graph, okay, between energy and time. Now
Right.
let's understand another graph. So this graph, it is a very particular, I mean specific graph, okay. It represents energy variation, I mean variation of kinetic energy and potential energy with respect to position. This is our main position. This is the, these are the, let's say this is x-axis, or it represents displacement, okay. So this is our extreme position. Okay, this axis represents energy. This graph represents potential energy, while this graph represents kinetic energy. So again, as you can see, when kinetic energy is zero, potential energy is maximum, right? And when potential energy is zero, kinetic energy is maximum here. And this black line represents total energy, okay, total mechanical energy. And you know total mechanical energy is kinetic energy plus potential energy, right? It is
Yes.
the summation of, so here basically energy gets conserved, right? So kinetic energy and potential energy and total energy as a function of time, as you can see, and a function of displacement, as you can see in this figure B, okay, this is figure A.
Uh,
The kinetic energy and potential energy both repeat after t by 2, and the total energy remains constant at all time and place, okay. Both potential and kinetic energy in SHM are seen to be always positive in figure, okay. Kinetic energy can never be negative, right? Because it is 1 half mv square. Mass can never be negative, and v square, that is the square of velocity, that will become positive after all. And potential energy is positive by choice of the undermined constant, okay, in potential energy. So both kinetic and potential energy reach maximum value twice. So average kinetic energy and average potential energy, if you want to write, then it will become half plus, sorry, 0 plus half kx square, ka square. So it gives us half ka square. And if we put the value of k, that is m omega, then it will become, this is 1 by 4, right?
right.
1 by 4 m omega square a square, that is half e, okay. So average kinetic energy is E by 2, and average potential energy also E by 2. Alright. So let's understand this concept by taking an example. Okay. So the question says a block whose mass is 2 kilogram is fastened to a spring. A spring constant is 100 Newton meter. It is pulled to a distance x is equal to 0.1 meter from its equilibrium position. At x is equal to 0 on a frictionless surface. From rest at t is equal to 0, calculate the kinetic energy of the block when it is 0.05 meter away from the mean position. This is the question. A block whose mass is 2 kg is fastened to a spring constant fastened to a spring whose spring constant is 100 Newton per meter. It is pulled to a distance of 0.1 meter from its equilibrium position at x is equal to 0 on a frictionless surface from rest at t is equal to 0. Calculate the kinetic energy of the block when it is 0.05 meter away from the mean position. So here 0.1 meter is our automatically becomes our amplitude, right? Because this is the maximum displacement. And we are required to find the kinetic energy when it is 0.05 meter away from the mean position. So this is our spring, okay? Here is our block, and this is the mean position, let's say, okay? X is equal to 0. Now what we are doing right now is we are stretching this spring. Yes or no?
Yes.
This displacement is our amplitude, right? That is 0.1 meter. We are required to find the kinetic energy when the block is at this position. Let's say this x position is 0.05 meter. So at this position we are required to find its kinetic energy. So how we are going to find the kinetic energy of this block? So first of all, let's find out its angular frequency. Okay. So angular frequency of this block would be under root k by m, right? Constant is given, that is 100, and mass is also given, I think 2 kg. So it will become under root 100 divided by 2. That is how much? Under root 50 or 5 root 2. Yes or no? that is approximately 7.07 radian per second. We found out the frequency. Now its displacement, if we want to write its displacement equation at any time, any time. So let's say it is a cos omega t. Why we have taken a cos omega t, not sin omega t? Because we are stretching it to the maximum, as you can see, then releasing it. Okay, so it is starting its motion from its extreme position. Yes or no? Here amplitude
Yes.
is 0.1 cos, and omega t, sorry, omega is 7.07 multiplied by t, right? Now when particle is at this position 0.05 meter, then from this we can find out the time, right? So if we plug this value here, it will become cos 7.07 t. Now 0.05 divided by 0.1 is 0.5 cos 7.07 t. Okay,
Okay.
and when it becomes cos 1, or we can write down sine function as well, right? I mean sine 7.7, if cos 7.07 t is 0.5, then that means sine 7.07 t is under root 3 by 2, right? 0.5 is nothing but 1 half, yes or no?
Yes.
And that is 0.866. Let's call it equation number 2. Now velocity at this position will be what? So if you differentiate this equation of displacement, we'll end up with a omega sine omega t, yes or no?
Yes.
Here a is 0.1, omega is 7.07, and sine omega t, that is 7.07 t, right? That value is nothing but this 0.866, yes or no? So from here, if you calculate these values, you'll end up with 0.61 meter per second. But that is what we need for the kinetic energy expression, yes or no?
Yes.
So basically, kinetic energy is what? Half mv square. So half multiplied by mass was 2 and v square, that is 0.61 square. That is basically 0.37. That is our answer. So what we did was, first of all, we found out the angular frequency. Okay, then we wrote down the displacement equation, and from here we found out the value of sine theta, right? Now we always knew that to that the expression for kinetic energy is half mv square, so we are gonna need velocity, right? So we wrote down the velocity equation, and by plugging these values we'll end up with velocity value, and by plugging this value in this expression we'll get our answer, yes or no? That's it. Let's take another question. Question says a particle executes simple harmonic motion with amplitude A and time period T when the displacement from the equilibrium position is half the amplitude. What fractions of the total energy are kinetic and potential? That's the question. A particle executes simple harmonic motion with amplitude A and time period T. So let's take a particle. Let's say this is our particle. And these are the extreme positions. Okay. Plus A and minus. Okay. Here time period is given, that is T. When the displacement from the equilibrium position is half of the amplitude. So let's say this is the displacement and that is the half of the amplitude. What fractions of the total energy are kinetic and potential energy? So we are required to find out the kinetic and potential energy in terms of total energy. You know that total energy is given by half k square, right? Remember,
Right.
that is kinetic energy plus potential energy. So we are required to find out kinetic and potential energy at this middle point. Okay. Now you are already familiar with the expression for potential energy, right? It was, what was the
Yes.
formula for potential energy? It was half kx square, yes or no?
Yes.
But here x is a by 2. So half k a by 2 whole square. That means 1 by 8 k square, right? Or 1 by 4 in the bracket half k square. Yes or no?
Yes.
This half k square is nothing but our total energy, right? So it is actually 1/4 of total energy. That means 25% of total energy. Yes or no? Now, if we talk about
Yes.
kinetic energy, so the expression for kinetic energy is half mv square, but will not get any information about. I mean, it is pretty difficult to find out the relation between total energy and kinetic energy from half k square, right? So instead of that, we can do this thing that we can find out kinetic energy by subtracting it from the total energy. Yes or no?
Right.
So it is actually E minus U. Now this is E and potential energy. Here it is 1 by 4 E. Yes or no? So that gives us 3 by 4 E. That is the 75% of total energy. That is the answer. Understood?
Yes.
Very good.